All right, so this is a recap of what we did in Chapter 6. In Chapter 6, all we talked about was enthalpy. Now we need to tie in two more concepts to get the entire thermodynamic picture straight in our heads. So the first law of thermodynamics came first, and the first law of thermodynamics is energy is conserved. And then once they were thinking about thermodynamics, they thought, oh, you know what, there's something even more fundamental, and that's called the zeroth law of thermodynamics. Heat always flows from the fat Russian to the snowbank. So we got that in our back pocket, always hot to cold. And here's the first law of thermodynamics. So when we talked about this first, we heavily emphasized that every thermodynamic event occurs between the system and the surroundings, and the system and the surroundings make up the universe. The universe. And energy will be conserved all the time. Now, if we're talking about a chemical system, there are two ways that we're going to lose or gain energy in our chemical system. There's heat, and then there's work. In chemistry, the only work that we're going to talk about is the change in volume due to a difference in pressure. Okay, that's the only work that can be done. A balloon expands. It does work on the surroundings. A balloon contracts. The surroundings does work on it. When we talk about heat in chemistry, we're going to use the term enthalpy, which is the heat of reaction. So in chemistry, we are talking about the change in energy of our system is equal to the change in enthalpy plus the work done. This delta E is a state function. A state function means that it doesn't matter how you get to this change of energy. All pathways lead to the same change in energy. It's analogous to say that we all are in this classroom that's given. We all came by a different pathway. End result, we're all here. Okay. Now, we're going to be talking about thermodynamics and spontaneity. Here's a warning for you. The AP folks have changed the word spontaneity. It won't be used. They have a new vocab word that they really like this year, and that vocab word is thermodynamically favored. So when I say spontaneous, you think thermodynamically favored. So a reaction that is spontaneous is one in which it will occur without outside intervention. Without outside intervention. Something that is non-spontaneous will not occur unless you do something to manipulate the circumstances. It is thermodynamically unfavored. It needs energy in order to get it to move. Yep? Okay. Let's take an example of this. If you have a piece of iron, anybody have a wrought iron fence? Okay, yours is probably covered with some sort of paint, yes? Because if you left it out there, the iron will react with the oxygen in the air and form iron 3 oxide. That happens spontaneously. You can't do anything, you don't have to do anything to it to make that occur. In fact, you have to do something to it to make it from occurring. Now, spontaneity or thermodynamically favored reactions can be looked at from this light. If the chemical potential energy of the reactants is greater than the chemical potential energy of the products, it will be generally thermodynamically favored. When I said that, you should have been thinking exothermic or endothermic? Exothermic. I want you to, on your notes right now, draw me a small diagram of an exothermic reaction, the potential energy of the reactants, the products, as time goes on. Here's the reactants, here's the products, the change in the potential energy of the products minus the reactants. Is the heat of reaction determines whether or not it is exothermic or endothermic. This is an exothermic reaction. The sign of delta H will be negative. Now, one thing kids get mixed up in their mind is they try to equate spontaneity or the thermodynamic favoring of a reaction with the rate of a reaction. This reaction, carbon in its diamond form, going to carbon as graphite, which is pencil lead, is spontaneous. It's going to happen without outside intervention. So diamonds are becoming pencils right this moment in time.
It's very slow, right?
And thankfully. And it's not measured in human time, it's measured in eons, which are really, really long time. So if we were to look at this reaction, the reactants become the products, the change in enthalpy would be products minus reactants. That is thermodynamically favored or thermodynamically not favored? Not favored. It doesn't say how long, if you added energy, it would take for this to happen. This determines how fast it happens. Are we clear? Got to separate those two constants. Or concepts. Oh, here's another vocab word for you. A thermodynamically favored reaction that does not proceed at a measurable rate, that would be the diamonds going to pencil lead, is said to be under kinetic control. Kinetic control. If you can't see it happening, it's kinetic control. Bet you that's on the AP test again. Okay, any spontaneous process is irreversible because there's a net release of energy when it proceeds in that direction. It'll just go that way. It's spontaneous in one direction. It is non-spontaneous in the other direction. If you want it to occur, what should you do? Add some energy. There you go. Add some energy. A reversible process will go back and forth between two end conditions, and a reversible process is at equilibrium. There's no change in energy there. It's just kind of like a tennis court and a ball bouncing back and forth, back and forth. So if it's spontaneous in one direction, thermodynamically favored in one direction, it is not thermodynamically favored in the other. Okay, here's a car rusting, spontaneous car going to rust. Here's non-spontaneous rusted car going to nice shiny car. All right, so we said that reactions are thermodynamically favored if there's a release of energy. So that what that means is, for the most part, an exothermic reaction happens spontaneously. However, endothermic reactions sometimes happen spontaneously as well. The one that comes to mind to me is a cold pack. When you crack a cold pack together, what you're doing is allowing the reactants to come together. And spontaneously, those reactants mix, form some products. That endothermic reaction is drawing in heat from the surroundings, which would be you. Yep. And it feels cold. Right. So how can something work like that when it's not favored by the heat exchange of the reaction? The answer to that question is it also depends on the entropy of the system, the entropy of the reactants in the products. Entropy, which actually was named so it sounded like enthalpy, to confuse all students, is also a state function, means that you can calculate it a number of ways, you come to the same end result, and it's a measure of the randomness or disorder of a system. In Chem 1 we talked about something that has high entropy, has high disorder. We need to refine the definition of disorder by saying disorder is the number of places or the number of positional arrangements that a system can have. What? The greater the possibilities of arrangements, the greater the entropy. Okay. Let's pretend you're particles and you are in this room. If I cut the size of this room down in half, I could pretty much guarantee where you would be in this room because there aren't a whole bunch of places for you to be, yes? Now, if I expanded this room to be the size of the school, there would be many more places for you to be. So the entropy of the giant room would be greater than the entropy of the small room. The universe really likes disorder. It takes a lot of energy to keep things ordered. You know this in your daily life. It is a royal, unfun time to fold your clothes into little packets of clothes and put them in their place, right? Some people, this is not me, but some people get great joy out of those little sock divider things, and all their stuff is just the, okay, they are into that order. I am not. It takes far less energy on my part to take the clothes out of the dryer and think, they can live in that basket for a while. That is quite disordered. It takes less energy to maintain disorder than it does to maintain order. Are we clear there? Okay. So, you can figure out the change in entropy of a system by taking the change in energy of the products, the final entropy, and subtract the change in entropy of the initial, the reactants. If something has a positive entropy, that process is generally spontaneous. If something has a negative entropy, that is a decrease in disorder, it is generally non-spontaneous. Here is an example about how that works for you. A kid I know was really excited to get the Hogwarts Lego set when he was about 6. Anybody remember the Hogwarts Lego set? 9 gazillion pieces. So it took him quite a bit of time during a Russian winter to put Hogwarts together. And then in a really weird thing, officials came into our apartment and they had to inspect it. There was nothing I could do about it. There were 3 of them, and they showed up and they had to go where the Hogwarts castle was. And we had built a little fence around the Hogwarts castle, and everyone was like, oh, look at that Hogwarts castle, it's great. 2 out of the 3 officials went around the little fence. The 3rd official kick the fire out of Hogwarts Castle and spread it all over the room. You think someone had hurt him bad. He was just like all upset, had to take him to another room. Don't be mean to the officials, you'll never know what happened. Anyway, he was really upset after Hogwarts Castle, and he put all of his Lego pieces into a big bin.
Why did they?
I don't know, to this day. I don't know. Okay, back to my entropy example. It was very, very little energy on the part of the surroundings to take the castle, kick it, and spread it into a million pieces, correct? Once it was in the giant tub of pieces, what is the likelihood of me taking that container of pieces, dumping it over, and having it fall out to an assembled Hogwarts castle? It ain't gonna happen, is it? It is not favored by the universe. I would like to see it. I think it would be very cool. If I did see it, I would think it was just a manipulation of a video. How about you? Because it's not gonna happen. All right. So what you are going to have to do is judge whether the system, the reactants of the products, are increasing in entropy or decreasing in entropy, and then make a value judgment about whether something will happen spontaneously or is thermodynamically favored. So here are some guidelines. Any change of state, like going from a solid to a liquid or gas, is a change in the positional arrangements of the particles. So there's a change in entropy. If you have a solid, it's kind of stuck where it is. There's very few places for those particles to be, very low entropy. A liquid, the particles are free to flow over each other. There's more entropy there, more places they could be. And finally, a gas is the highest entropy state that there can be. It's totally random, straight line motion, and it's constantly in motion. So as you change state, you change the amount of disorder. As you change temperature, you change the amount of disorder. How many people have a pet? How many people have noticed that when you take your pet to the vet, they know you're going to do it? They're waiting for it. So, you're like, okay, it's time to get the pet in the car carrier, let's go. What does the pet do? It runs away like crazy. It increases its kinetic energy, does it? No. When it increases its kinetic energy, it has more places it can be. It's under the table, it's on top of the table, it's in the refrigerator. So the entropy increases as the kinetic energy increases. Kinetic energy is tied to temperature. When solids dissolve, you take it out of its very ordered structure and you put it into a liquid structure that has more positions, more entropy. This is the big one. When the number of gas particles increase, what you're looking for here is the coefficients to tell you the number of moles. On the reactant side here, you have 2 moles of SO3 gas. On the product side, you have 3 moles of gas, 2 from the SO2 and 1 from the O2. Got that? Remember, each mole is 6.2 times 10 to the negative 23rd particles. There's a lot of particles to keep straight now, yes? So there are a lot of positions for a lot of particles. When molecular complexity increases, so does the entropy, because there's different ways that you can find the arrangement of the atoms. Only 2 atoms to arrange here, 3 atoms to arrange there. So it has a greater entropy here than there. And within a compound, more energy. These things kind of look the same to me. All right. So what you're going to be doing is predicting the sign. So solid sugar is added to water to form a solution. The system would be the sugar, and it started out as a solid, and then it went to an aqueous solution,
So the entropy increases.
the entropy increases. Iodine vapor condenses on a cold surface to form crystals. That is a decrease in entropy. Do you think that happens spontaneously? The opposite will occur spontaneously. Okay, we're going to do a little math. Remember that the change of entropy of a reaction equals the change of the products minus the change of the reactants. Your thermodynamic chart is based on 1 mole of each one of those substances. If you have more than 1 mole, you must multiply those values by the number of moles that you have. This answer is wrong. I don't even know why it's there. This is the answer I got. Okay.